Assalamualaikum and salam sejahtera. Hi everyone. Today is our first online class. Okay, let's start. We refer to the first slide. It can be seen here the learning outcome of this course. This particular chapter met with the learning outcome 2, which is by the end of this semester, the student should be able to analyze and solve deformation of structure member based on double integration and energy method. This week, we will cover Chapter 4 of Solid Mechanic 2, which is deflection of beam by using double integration method. Deflection of beam. These are the course outline. First, we will cover the deformation of beam under transverse loading, and the second one is the equation of elastic curve. You can see here the figure of experimental method in order to determine the deflection of beam due to the applied load. These are the few examples which will be explained later. Deformation of a beam under transverse loading, I will explain after this slide. Deformation of a beam under transverse loading. First, you have to state the relationship between bending moment and curvature for pure bending. The general equation is 1 over rho is equal to mx over EI. Okay. You have a simple example, cantilever beam with load P at the free end. I mark at the free end as A and fix end as B. The distance between A and B is L. So now you have to do the cross section in order to obtain the value of mx. So I do the cross section just before B. Counterclockwise is positive. Summation of moment is equal to 0. So the moment equation would be negative px minus mx is equal to 0. So you will obtain moment is equal to negative px. Substitute this moment value into the general equation. So now you have 1 over rho is equal to negative px over EI. Curvature varies linearly with x. How to solve this type of questions? And then now you have to apply the boundary condition. At A, x is equal to 0. You will get 1 over rho is equal to 0. So rho A, you will find rho A as infinity. At B point, x is equal to L. 1 over rho B is not equal to 0. When you substitute x is equal to L, you will find 1 over rho B is equal to negative PL over EI. Rearrange the equations. Rho B as your main function of your equation, so rho B is equal to EI over PL. For overhanging beam AD support concentrated load, so if you have this type of problem, what you should do first? First, you have to find the reaction at A and C, and then you have to draw the bending moment diagram. After draw the bending moment diagram, you can see at the point E, M is equal to 0. When the moment is equal to 0, the curvature is also equal to 0. From the bending moment diagram, you can see the maximum moment occur at point C. Substitute the maximum moment into the equation to develop elastic curve. Elastic curve is to determine the maximum deflection and slope of the beam. Okay class, there are several types of analysis in order to determine deflection and slope of the beam. In this chapter, we will learn two types of analysis. The first type is type 1, direct determination of elastic curve from the load distribution. I will explain what is the deflection and slope. The figure shows the deflection and slope of the beam. You can see here the deflection is referred to the y-axis and slope is referred to the theta. From elementary calculus, simplify the beam parameters. 1 over rho, you will get d2y by dx squared. Substituting and integrating into the elastic curve, you will get the formula as stated in the yellow box. If you want to find the slope of the beam, you have to integrate the second derivative of y into the elastic curve. If you want to find the deflection, so you have to double integrations of second derivative of y. C1 is referred to the constant value after integrating the second derivative of y, while C1x plus C2 is a constant when you do the double integration of second derivative of y. Constants are determined from boundary conditions. It is depend on loading type of the beam. The figure shows 3 cases for statically determinate beams. The first one is simply supported, second overhanging, and cantilever beam. As you can see here, at the support point, there is no deflection occur, and at the fixed support end, there is no deflection and no slope occur. For the example 9.01, we will discuss for the next sessions. Okay, we stop until here. If you have any queries, let me know. You may contact me through WhatsApp or email. Thank you.